Okay, we were talking last time, and we'd gotten to this page in the notes. We'd gotten to these situations. We'd previously been talking about situations where if I have a girder that looks something like it's fixed at the bottom and it's got a pin at the top, it's got a load on a P. What's the K for that? 0.7. Is it sway or no sway? No sway, right? Yeah. And then I have a situation that's like this. What's the K for this? Need to use the alignment chart. You need to use the alignment chart. Whenever you have a beam that's connected with a moment resisting connection, it's not a fixed connection up there. If it is, the beam would have to be like infinitely stiff. It's not. Okay. So you have to use the alignment chart. And that's what we're going to be talking about today. Introducing the alignment chart and then corrections to the alignment chart. Okay, so I introduced this. I said, what happens if we took a frame and I have connections here that are moment resisting connections? Remember, those aren't fixed. I mean, they're not fixed. They're not fixed connections. They're moment resisting connections. And how do we handle situations like this? And I'd say, well, it starts to play the what if game. Okay? If I sub B is really, really small, like a noodle, really, really thin, like nothing, then those columns are going to be deflecting like crazy. That beam's going to be whipping around looking like something like this. Okay? And it's going to almost be like as if that thing's not really there and it's pretty unstable. If I sub B is really, really small. But what if I sub B is just honking large? You know? It's just doesn't want to move. Okay? Well, the deflected shape is going to look something like that. It's going to approach a fixed connection, right? And we would say the K here is somewhere between 2 and 3, or close to 2. And somewhere here the K is between 3 and 10. And actually I've seen K's get as high as 20. Okay, that starts to get really scary when they get that high. Okay, but it's doable. As long as it's safe, it's doable. And how do we know? How do we know what it's going to be? Well, that's what we actually have to do is we actually have to look at the stiffness of the beam compared to the stiffness of the column. Okay? And we have to turn it into an equivalent rotational spring. We have to come up with an equivalent rotational spring for the top and an equivalent rotational spring for the bottom. And the cool thing about this is after we have this equivalent rotational spring, we can solve any problem. It doesn't matter what it looked like before. If you can lump it and turn it into an equivalent rotational spring on the top and the bottom, then it's all the same. It doesn't matter. It doesn't really matter if there was 10 beams or 2 beams or 1 beam that went into making this spring at the top. It just matters there was a beam and it has this stiffness. So what we're going to use this trick, this awesome, and every one of you should get your checkbooks out. And after writing your check, your yearly check to Oklahoma State University, with my name on it, of course, you should then write your check to the grandchildren of Jackson and Moreland, or probably the great-great-grandchildren of Jackson and Moreland, because especially if you're about to go work for a tower company, they will make your lives livable. Okay? Without it, you would not want to live your life. And because what you'd have to do is you'd have to do a differential equation every single time. Every single time you're going to try to solve one of these problems, and they kind of simplify things. Now to simplify it, they made the following assumptions. They basically the Jackson Moreland alignment chart, and these are two guys from Boston in about 1920s that determined this chart, this ability to determine the effective K from a situation like this. from a graphical solution to a differential equations of a column with two rotational springs with the following assumptions. And what they did, it's just amazing, because you flip over on this previous page, and these are in your manual. And I wouldn't draw on these, okay? I would photocopy these and save these for your grandchildren, okay? Because it's that amazing, okay? They're that awesome, because every single time you draw a line on this, I just solved a 5-page differential equation. Isn't that amazing? Thank you, Jackson Moreland. Thank you to your spirits. I appreciate that. You come in here with a G from the top. You come in with a G from the bottom. You draw a line. Boom! You get your K. Remember, there's going to be one of these charts, one of these differential equations for sway. There's going to be one of these charts, one of these differential equations for non-sway, for no sway. And every time we're going to need a G for the top column of the column, you're going to need a G for the bottom. You're going to, basically what you're doing is you're coming up with an equivalent rotational spring for the top and an equivalent rotational spring for the bottom. And what we're going to learn is when Jackson and Moreland derived their equation, it looks something like this. A GA and a B, because you need a G for the top, you need a G for the bottom. You draw the line in between, and booyah, you get the K. And they said that too. Okay, it was in their paper. Booyah. That's what you had to say every time you drew the line. And it looks something like this, but we're going to find in this class that we're going to quickly change. Okay, we're going to quickly change. And it's kind of weird, because if you look in your steel manual, you'll find this equation in it. You'll find the alignment charts on the previous page, but they are wrong. Dead wrong. And they need to change. But ASC won't change. Well, not quickly. But the reason they're wrong is because there was assumptions made, a few assumptions made during the Jackson and Moreland alignment chart. And we're going to talk about these assumptions here, and we're going to actually attack every one of these assumptions, and we're going to doctor the alignment chart, doctor this equation so we can address, or at least largely address, every one of the assumptions. Get way closer than what's out there right now. These assumptions: all columns and girders have the same modulus. Sounds like a good assumption. Guess what? It's wrong. Number 2, the girder stiffness every single time is 6 EI over L for sway cases and 2 EI over L for non-sway cases. And we'll talk about why those are wrong. There's an assumed deflected shape. If those deflected shapes are different, then that needs to be changed. This is the most common modification that's made to the alignment chart, and this is the one, if you are not careful, is extremely unconservative. It's not applied correctly. Number 3, no axial load in restraining members. And that sounds like a decent idea. We're going to find out that's wrong in this class, and we're going to address it and talk about how to deal with it. Number 4, all columns in a story buckle simultaneously. That's dead wrong. And we'll talk about how to handle it as well. And then number 5, total joint restraint is divided equally between columns. We're not going to talk as much about in this class because it takes a lot of iterations. But we will talk about it in general. We'll talk about it in general, what it's all about. But we'll find that the time it usually takes to get this correctly is not worth your efforts. Okay? It's just not worth it. You might save 10% by reducing your actual capacity by 10%. And and it might take you like 6 pages to get that 10%. Say, eesh, is that worth my time? Because that's really, when you go out and work, that's what it's about. There's time, and then there's results. And you want to minimize the amount of time you put in, and you want to maximize the results for that time. No one on earth will pay you the big bucks. Well, not no one, but not very likely will they pay you the big bucks to get the dead right answer. But they will pay you the big bucks to get very close and a very good answer quickly. That's what it's all about. That's what life in the engineering world is all about. And number 5 is just not justified. Okay? It's just not justifiable. You really just might as well solve a differential equation. Nobody wants to do that anyway. So, we talked about these amazing tables, okay? And when we have things that are pinned, they have a higher G value, or they're more flexible. We would say a pin has a G value of infinity. When we actually have a fixed connection, we would have a G value of 0. Talked about that page. Booyah. Now, the actual alignment chart equations, if one was ever a masochist. You know what masochists are? They like pain, right? They like pain, and anyone that gets a PhD is someone that's a bit of a masochist, okay? But those folks love these type of equations, right? Where you have a G top and a G bottom, and you can solve for a K. And notice there's a K here, there's a K here, there's a K here, there's a K here, there's a K here. This is actually the general solution to the differential equation of the spring at the top and the bottom. Okay? And this is what the alignment chart solves for you. Imagine having to solve for the K's. I mean, you can't even solve them. You can't even isolate them because they're basically in every single variable, and that's what the alignment chart does for you. Okay? It solves this equation for no sway, and it solves this equation for sway. You with me? Yes. It's pretty awesome. While the alignment chart is very useful in the previous form, it has basically, it's sad, but extremely limited applications. It's actually only limited, it only can be used as it's written if every column is the same size. Every connection is a moment-resisting connection. Every load on each column is the same, and you only are dealing with one-story structures. Not very useful. But don't worry, we're going to figure out how to make it right. Oh, I said, in fact, it only applies to one-story structures with moment connections at each joint, equal loadings on each column, and actually each column has to be the same size, too. Okay? It's the only way it truly works. However, with some slight modifications, we can make it way more accurate, and that's the magic we're going to be working in this class. We're going to talk about assumption number 1. All girders and columns have the same modulus. And I bet at the beginning of the class, or if you haven't seen something like this, you just said, "Chad, that's a great assumption. All modulus, what's the modulus of steel? 29,000 KSI, right?" Oh, you're wrong in certain circumstances. For lightly loaded columns, this is a great assumption. A dead-on good assumption. For medium to highly loaded columns, this is a bad assumption. And it's not that the modulus changes, ladies and gentlemen. It's that the effective modulus changes. And I'll explain that in the next couple pages. All rolled and built up sections, everything made out of steel, actually everything made out of just about every single material on the face of the earth that's not highly modified, is built with these things called residual stresses. And in steel, what they come from is the cooling and rolling process. If you can imagine, when this steel member comes out of the rolling process, we have chunks of steel here that are a little thicker. So they're going to cool at a different rate than the chunks of steel here, here, and here. Because of that, there would be built-in stresses inside of our member. Built-in stresses. It looks something like this on the bottom flange. It looks something like this. You say, well, what do you mean built-in stresses? I mean, if a steel shape is sitting on the countertop here with no load on it whatsoever, what's the overall stress? It's not flying through space. If it's not being loaded, the stress is 0, right? Has to be 0, right? And it still is. But these residual stresses cancel each other out. If you have compression, high amounts of compression in some areas, you have to have high amounts of tension in other areas. So again, they cancel each other out, but they're still there. They're still there. They still exist. And in welded shapes, it's even weirder. Because not only do you have residual stresses from these plates to begin with, but when you do the welds, they totally warp and change what your residual stresses look like. You're like, what? Why have I never thought about these before? Well, if you had me previously from steel, we did talk about them when it comes to columns. But if you haven't, you'd be like, you were cheated, basically. Okay? No. You didn't have to worry much about them, because when it came to failure, They weren't that big of a deal until now. They weren't that big of a deal until it came to columns. But now they've become a big deal. When these sections are loaded, actually portions of the cross-section begin to yield. This is the reason they don't follow the Euler buckling curve. Remember how we talk about there's a mathematical crushing, a mathematical buckling equation, but our real test at it doesn't follow that. And one reason why is residual stresses, imperfections, imperfect loadings. Residual stresses is a biggie, a real biggie. Okay? And we're going to actually have to start taking that into account. Take into account these residual stresses. So we're not able to get what we think will happen because these residual stresses cause things to happen first. What? What am I talking about? Sounds like I'm talking some like crazy talk. Well, I am. But let's talk about, it does have some applications here. I'm going to show you, I'm not going to go through all the details. You can look at these on your own. But I'm going to take a plate of steel. We can imagine this being some more complicated section. We can imagine the residual stresses being more complicated, but I'm not sure why you'd want to. If you can explain things simply, why the hell not, right? So let's start out with just a very typical steel plate, and we're going to take it through this stress-strain curve. Ugh, this is typical. We know this. This is boring, dumb. Oh, we're going to add something to it. This plate's going to have some residual stresses in it because of the cooling process. It's going to have tension and compression. So the outside parts of the member started to cool first. They start to shorten. It's going to put the member in tension. You with me? Great. Tension and compression. So under no load whatsoever, and this, believe it or not, happens in every single piece of steel on the earth. The only way you could make this not happen is if you took it all up to the same temperature and you cooled it ever so slowly. So every single ounce of steel experienced the exact temperature, and you brought it down very carefully over days. Doesn't sound very practical, does it? When they make steel, they roll it and they just throw it in the warehouse and let it cool. Okay? They actually put quench it with a bunch of treating material. They spray a bunch of chemicals and stuff on it to actually harden the steel, actually make it have more ductility. But that's neither here nor there. So they don't build them like they need to make perfect without any residual stresses. But it's okay. We just have to learn how to live with it. So as I start loading this member up, what happens, and as I start moving along this curve, nothing happens at first. We start loading it up until the very tips out here. The stress diagram isn't constant. I mean, we would usually think if we put some kind of P on it, some kind of axial load on it, would be P over A would be the stress, right? And the average stress, that's right. The average P over A, that's right. If I averaged every point along this curve, it would be along this line. It just so happens that never happens in real life. You have some points that are higher stressed and some points that are lower stressed because of residual stresses. And as you start increasing this more and more, you start to hit, this point starts to hit the residual stresses. First, it hit this point where the residual stresses plus the axial load causes it to start to yield. Well, what's that mean? Well, as we keep increasing the load, that means that stress cannot go any higher. It stops right there. As we start increasing the load, again, the stress goes higher, but that part's not. Now, when something hits yield, what do we know? What do we know what happens to the stiffness? It's nothing. It's nothing. It's almost as if it's not even there. In this situation for this column, when we look at stress, it's P over A, right? Right? So if something has lost all stiffness, can it take any more load? Somebody is drunk, and you go to punch them. Can you hurt them? No. They're stiff. They're not stiff. They're all flexible. You punch them, and then woo! They fly around. That's why in a bar fight they never get hurt. So how do you hurt them? You get somebody behind them to hold them, right? Right? To hold them in place. So when you punch them in the gut, like that drunk person takes some damage. You increase their stiffness, right? That's right. How to win bar fights. That's what you learned in advanced steel today, right? Can't wait to see that on the evaluation sheet. Anyway, when we get to this point where this material has lost its stiffness, it's like it's not even there. It's like the area is gone. Does that make sense? But we don't do that. The area didn't leave. So what we do instead is act like stiffness. The modulus in that area, the E in this area is 0. What's the E in this area? 29,000 KSI. Does that make sense? So what's the actual E? Well, it's the weighted average between these. You would take the area of this multiplied by 0 plus the area of this multiplied by 29,000 divided by the total area, and that will give you your actual effective stiffness. So we're going to keep going on along the same thing happening over and over and over and over again, and we keep going until this point, until our cross-section is 100% yielded. And structural resiliency tells us that that is the end of the road. Everything is at its limit state. But if we drew a picture of stress for a strain, ideally with a perfect member, we would say it would go up and up and up and kick over. But it doesn't happen that way. If we truly measured the strains, if we truly measured what the deflection for the stress strain is, it's not going to happen that way at all. That after you get to about, I think it's around 44% of your yield, 0.44 times Fy, that's when this starts to no longer be linear anymore. That's when all of a sudden you start to get some nonlinear portions. You start to get some areas that are yielded in your cross-section. Depends on the residual stresses. Depends on the size of the member and the type of the member. Okay? We don't like to think about that. We just like to go on. What will happen is our stiffness will change. What do I mean? The slope of this line changes. Does that make sense? When the slope of the line changes, that means the stiffness is going to change. That means that initial assumption that the modulus of the girder and the modulus of the beam or the modulus of all columns are the same. It's not right. Because if you get this area above 0.44 Fy, it doesn't apply anymore. You actually have to reduce it. You have to reduce your modulus. Because of residual stresses, the stress first strain ideal is not equal to the stress first strain actual. Therefore, a modified EI should be used at high loads. This is why columns do not follow, or one of the reasons why columns do not follow the Euler buckling load. It's why these things start to go down, why these things start to change. Awesome. Now, there was a sheet on the back that you can't read. Apologize for that. So I have it printed again on top of our new set of notes. Okay, so we're not going to cover everything. We're going to get started, though, just a little bit. Spend about 5 more minutes talking about this, then we'll stop. But recall that assumption 1 that the one we were just talking about, was this E girder is equal to this E column. And for low-loaded columns, that's a great assumption. But for high-loaded columns, as I just showed on the previous page, bad assumption. Bad assumption. And so if we can think of this, bringing this E back, and E on the top and E on the bottom, we're going to use something called the tau factor. What the tau factor does is it's really the ratio of the actual E over the ideal E. Okay, and we're going to use the tau factor. And there's a table in your manual, table 421, and it used to be on page 4317. I think it still is, but you should check it. It's close to that at least. And it gives you the tau for different Fy and stresses. So this is pretty cool. This means all I need is P over A. All I need is to look up the stress on my column. And I go up and I look at it in the chart, and it gives me a tau factor. Tau factors are going to be anywhere between 1 and very low numbers. Okay? And what they do is they modify the stiffness of your column. And you'll have a tau factor for each column. Kind of. That's going to change as well. You're going to have a tau factor that goes in the numerator. Does that make sense? So, I'll ask the question again. All we've done here is we've modified this g. We've just modified it by adding a tau factor to the numerator. For what you know now, you'll use a tau factor on every column. So if I have a joint here, I have some structure. Say it looks like that. I'm not sure. I don't like that structure, so I'm adding another column there. Let's say I have a load here, and I'm looking for the k of this column. So when it comes to, I have my g bottom. My g bottom is going to be equal to what? Infinity. Infinity. And when it comes to the top, I have to solve for a g. And I'm going to have this summation of I over L of my columns. And for now, this is going to change in a little bit. For now, you'll have a column on the top and a column on the bottom. Yeah? And you'd find a tau for the top, and you'd find a tau for the bottom. Right? And that's going to go in the numerator. Yeah? And then you go for the denominator of the G. And there's beams. There's a beam here and a beam here. So you're going to find the I over L for the beams on both sides. If you've never used the alignment chart, you probably should open a book. Probably should, make sure you really look at this hard, okay? Because it's a little odd, but it's pretty powerful and important. I think that's a good stopping place for today. Is there any questions about the tau factor? Any of that stuff right now? All you're doing when you use the tau factor, remember, G is all about accounting for stiffness. It's accounting for stiffness at this joint. The equivalent rotational stiffness at that joint. The tau factor, all it's doing is it's discounting the contribution of the columns to that stiffness. Remember, I, that's a stiffness term, L, that's a stiffness term, and E is a stiffness term. And we're discounting the contribution of the E to the stiffness at that joint from the columns. Okay? And everything's going to be changing. We're going to keep morphing this equation. This original equation is going to morph and morph and morph and morph over and over and over and over again. Okay? Keep being modified.